So in this video, we're going to talk about a little bit more how to characterize current a little bit more. But I wanted to start off with this this graphic, this thing I scribbled down from the last video, where we were talking about the path that a charge carrier takes as it tries to navigate all the stuff in its way as it moves down a wire, right? So you can think of this as the last time you were in a really crowded room and you needed to get across the room. Maybe you were at a club and there was a crowded dance floor, or there were a lot of people there. Maybe you're at a wedding or a family reunion and everybody was kind of clustered up into one little room and you really needed to get across. How did you get there, right? You didn't take a straight path. You probably had to bounce around a little bit, hopefully not physically, but if it's a crowded dance floor, maybe. But you have to go here, and maybe you got to talk to your Aunt Mildred, and over here, and get around your cousins, and over here, and this guy that's trying to dance with you, and you got to, whatever. You got to get across, but to get from here to here, there is some resistance. Now, we talked about this in terms of how fast these things move, but you can think about this in terms of that there is something resisting the flow of charges, right? There is something in the way. In this case, lots of things in the way, but you can characterize this as resistance. And you can go farther with that, right? If this is a very orderly gathering and people are standing in rows, then there's very little resistance. You can kind of just go straight. But if it's kind of chaotic, if there are lots of people in the way, then you can't. You've got to move around. And so resistance depends upon physical structures. And we're also going to find out it depends on things like temperature and all that good stuff. But in general, the physical structure of this conductor contributes, in fact, determines the resistance to the flow of charges. So resistance to the flow is what we're going to be talking about in this video. So let's talk about how to symbolize that. Oh, come on, paper, stay. All right. So the symbol for resistance is just a capital R. We read this as resistance. The unit of resistance is called the ohm. We will write that as a capital omega. Omega is the Greek O, right? This is a capital omega. This is probably no news on campuses such as ours with a large presence of Greek organizations. We know what omegas are. The unit is called the ohm, and we use because we can't use capital English O because it looks way too much like a zero, right? So we got to use the Greek O to talk about ohms. The resistance is measured in ohms. And this is basically just a characterization of how well a material allows charges to flow through it. All right, so let's think about the current here. We know that the current is going to be inversely proportional. This is the mathematical symbol for proportionality. It's going to be inversely proportional to the resistance, right? The lower the resistance, the easier it is for charges to flow, the higher the current. The higher the resistance, the harder it is for charges to flow, the lower the current. So inversely proportional to the resistance. And we can probably do some further work and think that, all right, why is the current flowing in the first place? The current is flowing because there's a potential difference across the ends of the wire. Somebody put a voltage on it, right? Somebody connected it to a battery or plugged it into the wall or, hooked it up to a little wheel with a hamster running in it, whatever. There is some sort of voltage. And if I have a larger battery, a larger voltage source, I'm going to get more current. That just makes some sense, right? And so it's going to be directly proportional to V. It's going to be inversely proportional to the resistance. We can actually put those together really, really easily. Not always as easy to do it, but we can characterize this here in what we call Ohm's law. Now, this is expressed in terms of V, and I've been doing it in terms of I, but if I solve this expression for I, I'm going to get V over R, which is directly proportional to the voltage, inversely proportional to the resistance. This is what's called Ohm's law, right? And this is going to be our main tool for characterizing circuits in the same, or I should say, characterizing circuits with resistors in the same way that we characterize circuits with capacitors in the last chapter. For that, we use the definition of capacitance. For this, we're going to use Ohm's law. They're very similar equations. They're not mathematically complicated. The complications come in understanding how to apply it. But this is a workhorse in any course dealing with electricity. Ohm's law. V is equal to IR. All right, so that's all for Ohm's law. It's a pretty simple expression. We're going to see it used in some examples in later videos.